Hi everyone, it's Mr. H here, and welcome to this video on day 2 of using Newton's laws. Now what we're going to look at today is bringing in the 5 equations of motion into these laws that we looked at yesterday. And so we're going to look specifically at kinematics applied to forces with these 5 equations of motion. And so one thing that we're going to note is that the net force at different times is going to remain constant. So that's something that's going to help us out. It's not going to be changing, otherwise it would just change too many variables in our calculations. And I want us to consider if a car is speeding up on a highway, there's an original net force acting on the car. When you set cruise control on as you drive, the net force changes. All right, if you're moving at a constant velocity, there's a force of friction acting backwards, there's an applied force acting forwards, and you're not accelerating, therefore there's zero net force. When you slow down again, that net force is acting to oppose your motion, and that again we're going to assume is constant in that time. And so we're going to look at a situation now that doesn't have to do with speeding up and slowing down and driving at a constant velocity on a highway, but we're going to deal with someone pushing off the boards as a skater, gliding across the ice, and then slowing down and coming to a rest. So very similar to that situation. So the question says this: starting from rest, an ice skater, 54 kilograms, pushes off the boards with a force of 130 newtons west, moves 0.704 meters. He then moves at a constant velocity for 4 seconds before he digs in his skates and starts to slow down. When he digs in his skates, he causes a net force of 38 newtons west to slow him down until he stops. We're to determine the acceleration of the skater at each of these positions. So when he's first starting to accelerate, when he's moving at a constant velocity, and then when he begins to slow down. And then how far does he actually move? So let's see what we get. The first part, as we always have to do for these types of problems, is drawing a free body diagram. So we're going to go ahead and draw the FBD of the skater. And so because there's just one skater, the free body diagram should be relatively straightforward. It's just some of the calculations that we have to bring in a 5 equation of motion for. So in this case, free body diagram, if he's pushing off the boards, we know that he's pushing with a force that's in the westwards direction. That means, if you think about it, that there's going to be a counteractive force of 130 newtons pushing him in the eastward direction. So he pushes west, this east force pushes him in this direction. So this is the applied force of the boards on him. And then we have this normal force, and we have this force of gravity. And these are equal and opposite because he's not accelerating up or down. We're assuming he's not falling through the ice. So that's what we have. So we know a few things here. We know that the net force, we know that applied force is 130 newtons east. So we know that. We also know that the mass is 54 kilograms. And we know how far he pushes that force. So as he's pushing against the boards, he's going to move a displacement of 0.704 meters. So we don't even need that displacement for this first part because all it's asking us for is the acceleration of the skater. And so as we've always done for these types of questions, we go the net force is equal to the mass times acceleration. We know the net force is that applied force. And if we're trying to figure out the acceleration, we're going to divide both sides by the mass. And so the acceleration is 130 newtons east divided by 54 kilograms. And that gives us an acceleration of 2.407 meters per second squared in the eastward direction, or the positive direction. And so because we've indicated this positive direction here, if you just let it be positive, you'd know it was east. So we would conclude with a therefore statement and move on to the next part. In the next part, it's asking us just after he stops pushing on the boards, what's his acceleration? Well, we know just intuitively that if there's no more net force, right? And we can see this by drawing a free body diagram. The only forces acting on him after he pushes on the boards, we're assuming friction is negligible, are those two forces. So the no net force, then we have no acceleration. So that's pretty straightforward to answer that one. Now for the third part, it's asking when he starts to slow down. And so again, we can draw the free body diagram for the situation. In this case, he's slowing down, and so we know that he's causes a net force of 38 newtons to slow him down. Therefore, that's the applied force that's slowing him down. Force of friction, applied force, whatever you want to call it in this case. It's a little ambiguous, I suppose. But it's a force in that direction. Because he's moving in this direction, right? He's moving in this direction, and he's slowing down. So his acceleration is actually in the opposite direction of his movement, as we would expect. So there's where it's going to be. So let's say that there's the positive direction is the direction he's moving in. So then we do the same thing again. While we say we know that that applied force is 38 newtons west. So we're going to say it's minus 38 newtons. And we know the mass is 54 kilograms. We don't know the acceleration. And so again, it's just a matter of going to Newton's second law, F net equals ma, and figuring out that acceleration. So acceleration is that applied force in this case, which is different than it was before, right? Very different, divided by the mass. So we sub those things in. It's negative 38.0 newtons divided by 54.0 kilograms. And our acceleration, as he slows down, is 0.704 meters per second squared. And that's a negative, meaning he's accelerating in the westward direction. He's accelerating in the opposite direction of his motion. Now, that number, if you go back to the givens in the problem, looks very similar to this 0.704 that we had for how far he moves during that initial force. And so we're going to see if that's related or not. So this first part should have been relatively straightforward. It's the second part of the problem, part B, where things get complicated. So let's look at this. How far does he move? So the first thing I want us to notice here is that we have to look at the part where he's pushing off the boards. We have to look at the part where he's gliding. And we have to look at the part where he's slowing down. So here are the boards. There's some distance that he is pushing. Then there's some more distance where he's gliding. And then he slows down to a stop. And we have to analyze all those different things and add them all together to actually decide what the final answer is for this question. And just reminding you what the question was, it was asking this. How far does he move? Well, we're told initially that as he's pushing, that this displacement, as he's pushing, is 0.704 meters east. Easy peasy. We've already got that piece of information. We don't need any other piece of information for that first pushing segment of it. We also know during this pushing segment that he's moving with an acceleration of 2.407 meters per second squared east. We know that he glides for 4 seconds. He's gliding here for 4 seconds. We know that against the boards, his initial velocity is 0 meters per second. We don't know his final velocity, but we know his initial velocity. We also know that his acceleration while he slows down is negative 0.704 meters per second squared. So what we have to do is we have to put all these pieces together. We also know the final velocity here is 0 meters per second. So we just lay out the problem. Okay, what are all the things that I know and that I can solve? Beyond that, we know nothing more. What we need to find here, we'll call this delta D1 for the pushing part, we'll call this delta D2 for the gliding part, and we'll call this delta D3 for the slowing down part. So somehow we have to do something to allow us to figure out each of these things. Now, the problem here is that I only have one thing that I know in the gliding part, and we know that there's no acceleration, but we do know, in terms of moving at a constant velocity, that the displacement is equal to the velocity, whatever the velocity is, times the time. And we also know over here that it's going to be accelerating, so we need to use something that gives us 3 of 4 variables. So we have to find a fourth variable that we know. We only know 2 of them right now. So this is the big 5 that we're going to have to use. One of the big 5. So here's the strategy that we need to use. If we can figure out this velocity based on what we had in the beginning, because this should be enough information to give us the final velocity, because the final velocity right there is the velocity that's going to glide at. And if we can find that final velocity, then we have enough information to know the final velocity here. That's going to be the same thing because it glides at a constant velocity. And then we'll have enough information to solve this. This would be considered our v initial in this case. So we'd have v initial, v final, acceleration, and we wouldn't know the delta d. So literally we have to start by working from what the pieces that we know and work all the way through this. We can't solve the slowing down until we've solved the gliding. And we can't solve the gliding until we've solved the pushing. So let's go ahead and start with the pushing. So as we push, we've noted that we have to find v final. V final can be found using this formula. V final squared equals v initial squared plus 2 times the acceleration times the change in displacement. Well, we know in this case that it's starting from 0, so there's no initial velocity. So it's the square root of 2 times the acceleration, and the acceleration along that point was 2.407 meters per second squared, positive because it was in the eastward direction. And the displacement was 0.704 meters, again positive in the eastward direction. And so v final, we can add a vector to this because we know it's going to be in the positive direction, ends up being 1.841 meters per second east. So we move from the pushing to the gliding. And in terms of the gliding, we know what's going to happen here. We know that that final velocity that we found there is the velocity that's constant. It's not changing. There's no acceleration. And that's going to be 1.841 meters per second. And we know that delta d is velocity times the change in time. So it's just rearranging the definition of velocity as we did for projectiles. Right? And so it's 1.841 meters per second times the change in time. And the change in time we're told was 4 seconds, which gives us a displacement along the gliding section of 7.364 meters. And this, just to be clear, we gave a subscript here. We call this delta D2. So it's the second displacement here along the gliding section. So the displacement there is 7.364 meters. We knew from before, we were given that the displacement along the pushing section was 0.704 meters. So the only other displacement we now need to find is that third displacement along that last bit. So let's go ahead and solve for that. We know that slowing down, we knew acceleration, we knew v final, we didn't know v initial, but v initial is equal to the v, the speed, when gliding. And so that speed was 1.841 meters per second. We also knew the acceleration. We were given that to be 0.704. And the final velocity we're given to be 0 meters per second. All we need to find here is delta d along that segment. Delta d3 is what I've labeled that as. And so again, it's using the equation of motion that incorporates v initial, v final, acceleration, and change in displacement. That's the same equation we had up above, where in this case, it's not the v initial that's 0, it's the v final that's 0. And so we're rearranging for delta d. We're going to get negative vi squared is 2 times a times delta d. We're doing for the third one. So I'm going to divide by 2 times acceleration, and that's going to get me my delta d. So my delta d3 is going to be v initial, negative v initial. So v initial was 1.841 meters per second. And I'm going to divide that by 2 times the acceleration. The acceleration is also negative. And so this equation is made up in such a way that you don't have vectors on those, but it makes sure the negative cancels out properly to give you a positive displacement here, because we're moving a positive displacement forward. And what you get is 1.308 meters forward, positive value. And then it's just a matter of adding all those together. And so we could say the total displacement is something that is equal to adding up all those displacements, delta D1 plus delta D2 plus delta D3. And it's very clear what those are. When you add those together, you get a total of 9.38 meters, and it's positive, so it's east. So you've moved 9.38 meters east over that time. So that's how you have to do that. You have to piece the question out. There's 3 pieces to the question. Look at each part and determine, what can I solve based on what I know? If you can't solve it, move to a different part of the problem. Good luck with that. Any questions, feel free to reach out and ask for help.